Today we're going to graph complex numbers, to which one might respond by saying or asking, how do you graph something that's not real when we don't even know what the square root of -1 actually means? How in the world do you graph it? All right, let's find out. It can be done. Here we have a real number line. I know how to graph all the real numbers. I can find -4. It's right there. I can graph 6. It's right there. I can graph rational numbers such as 3.7. 3.7 might be right about there. I can graph irrational numbers such as the square root of 2, which is about 1.4 someplace around here. Yes, it may be irrational, but it has a place on the real number line. I can graph pi, about 3.14, whatever, which is right around here someplace. Again, it may be irrational, but it has a place on the number line. So I can graph any real number on the number line. But where in the world am I going to graph something like 4i? Well, it's simply not on the number line. Then where is it? Oh, I'm glad you asked. We can't put it on this line because this line is just reserved for real numbers. So the imaginary numbers have to go, well, someplace else. Someplace else. Someplace else. So now we're going to repurpose the coordinate plane. This thing we used to call the x-axis now becomes the real axis. And this thing that we used to call the y-axis now becomes the imaginary axis. So the real number 6 is still found right here. The real number -5 is still found right there on the real axis. But the imaginary number, 4i, oops, can't fit it on here. How about 2i? This is the imaginary axis, so the imaginary number 2i, which has no place on the real number line, we locate it here. That's 2i. 2i. How do we do something like 5 plus 2i? 5 plus 2i has the real part and the imaginary part. Yes, we're going to graph 5 plus 2i as if it were the ordered pair 5, 2. 5 on the real axis, 2 on the imaginary axis. So the complex number 5 plus 2i is located at 5 plus 2i. That is 5 plus 2i, the complex number. Notice that it is certainly not on the real axis because it's not a real number. It's also not on the imaginary axis because it's not what we call a pure imaginary number. It's a mixture of of imaginary plus real. It is indeed complex. It is imaginary, but it's just not pure imaginary. And so it's located neither on the real axis nor on the imaginary axis. It's over here. Kind of gives a new meaning to this concept of complex numbers and imaginary numbers. We can graph them. If I wanted to graph, how about 3 minus 1i? 3 minus I. We would locate that at 1, 2, 3 on the real axis, minus 1i on the imaginary axis. There's the number 3 minus I. Located on the ordinary complex plane as 3, -1. 3, -1. Yes, we can use ordered pairs to represent complex numbers. 3, -1. Simple enough, right? Right. Now let me show you something the book does not present. At least the book does not present it. Put that 6 back there. I don't really need it, but get rid of that dot and get rid of that. Get rid of all this. Fix that 5. Okay. So I want to show you something that the book does not present. I think the book presents this later in some other chapter, but I show it to you now because it's kind of cool. How do you do 2 plus, now let's do 3 plus 2i, and let's add to that, let's add 2 plus 1i. Alright, that's simple enough, right? We've done these. Just add the real parts, that's going to be 5. And add the imaginary parts, that's going to be 2i plus 1i is 3i. We get the complex number 5 plus 3i. Worth noting, by the way, that when you add two complex numbers, guess what you get? You get another complex number. Always. We say the set of complex numbers is closed under addition. It's also closed under subtraction. We're going to see in the next section that it's also closed under multiplication and even division. Closed means if you perform the operation on two complex numbers, you get another complex number. It doesn't jump out and give you something new. No, it's going to give you another complex number. All right, so I want to show you something neat now. That you say, well, that's not new. No, that's not new. Let me show you what's new. Let's graph these two numbers. 3 plus 2i right there. And we're going to graph 2 plus 1i right there. And I see now that my choices of numbers were not the greatest. This is going to be a little bit awkward. I should have done it a little bit differently. But it'll have to do for now. I'll give you another example in a moment. But if I now do this clever thing, physics people, tune into this. We're going to draw an arrow from the origin to this complex number. In physics, we call that a vector. A vector has a magnitude, a length, and a direction. That direction and that long. That's called a vector. 2 plus I can be represented by this vector. Now, physics people, you may remember there are a couple of ways to add two vectors. We can add a vector by creating a parallelogram, or we can add vectors by grabbing one of them and moving it up here. We call that connecting them tip to tail. The place where we end up, right there, that becomes the sum of the two vectors. Well, guess where we just ended up? We ended up at 5 plus 3i. So we can add vectors by making them into complex numbers and adding the complex numbers, and behold, we just also demonstrated something else kind of cool. Is not this represented by the ordered pair 3, 2? And this is the ordered pair 2, 1. Have you ever thought about adding ordered pairs before? We can now add ordered pairs. The ordered pair 3, 2 plus the ordered pair 2, 1 does indeed give the ordered pair 5, 3. And we see it right here by converting them to vectors and adding the vectors. 3, 2 plus 2, 1 gives us 5, 3. Just to emphasize the point, let me show you. Let's get all this is. Let me show you the other way to add vectors. And this is not the greatest example of it. Hey, let's switch examples. Instead of sticking with a poor example, let's make up one that'll work better. How about if we add, let's do 3 plus I, and to 3 plus I, we're going to add 2 plus 3I. All right, let's do that one. We're going to take, let's do the originals in yellow. We're going to take 3 plus I, 3 plus 1I, right there, make it into a vector. We're going to add to it 2 plus 3I, 2 plus 3I, right there, make that into a vector. Yes, we could pick up this guy and move it up here, and that would work great. But there's another way to do it. The parallelogram rule. The parallelogram rule is the way that we used most often in physics. We're going to create, let's see, how do I want to go about this? I think the easiest way will be to select this vector and make a copy of it. All right, so I have a copy of this guy. I'm going to take that copy. I don't need the, there we go. I'm going to take that copy, and I'm going to move it up here like this, so it's parallel to this one. Then I'm going to make a copy of this one. You said, but you're doing the same thing. Yeah, basically, yes. And I'm going to take this guy and make one parallel to it through this point. I get a parallelogram. The sum of these two vectors will be the diagonal of the parallelogram from here to here. That's the sum of the two vectors. So 3 plus I added to 2 plus 3I should give us, where are we? We're at 5 plus 4I. The vector 5 plus 4I. And indeed, yes, of course, 3 plus 2 is 5. I plus 3I is 4I. We have added two vectors using the parallelogram rule. Or we can add them using the tip-to-tail rule. Or we can add them as ordered pairs. 3, 1, plus 2, 3 gives us 5, 4. So we're adding ordered pairs. Pretty cool. Okay, so that's something that's not in the book, and I will not be testing you on, and it will not be in the homework. But graphing imaginary numbers certainly will. On the homework, by the way, you're going to be given, if you take a peek at it now, you might as well. If you look at page 325, numbers 2 and 4 will be assigned. On 2 and 4, for number 2, you're to use real graph paper, no faking it with regular notebook paper. On real graph paper, you'll set up your coordinate plane. And for number 2, you'll simply graph all 3 complex numbers. Dot, dot, dot in the correct locations. That's it. Then for number 4, you'll set up a new coordinate plane. Yes, a second coordinate plane. And on that second coordinate plane, you will graph those 3 complex numbers. Dot, 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 wherever they belong. You're done. Hey, you want to make them into vectors and draw the arrows? Fine. But we're not talking about vectors officially here in this section. So just 3 dots. 3 dots for number 2, 3 dots on a separate plane for number 4. No, you don't have to do 6 separate complex number planes. No, you only need 2. All right, clear enough? Clear enough, good. Let's move on. What does absolute value mean? Yeah, you've known for a long time, absolute value means distance from 0. That's why the absolute value of 5 is 5. Because how far away from 0 is 5? 5 units away. How far away from 0 is negative 5? Negative 5 is also 5 units away from 0. So the absolute value of 5 is 5, and the absolute value of negative 5 is also 5. Distance from 0. The simple way to think of absolute value, of course, in that context is just make it positive. That simple rule changes a bit when we're talking about the absolute value of complex numbers. It's still defined as the distance from 0. Actually, where is 0? The distance from the origin. Let's see how that works. Let's figure out the absolute value of 4 plus 3i. First of all, where is 4 plus 3i? 1, 2, 3, 4 plus 1, 2, 3i, right there. 4 plus 3i. We want its absolute value. Oh, I've seen students who don't pay attention in class, who do all kinds of weird things, and they say, oh, well, just make everything positive. And they say, it must be 4 plus 3i, it's already positive. No, no, no. Pay close attention to this. Absolute value still means distance from 0. There is 0 in the complex plane. 0 plus 0i. Right there, 0. We want this distance. Okay, want to make it into a vector? Be consistent here. We want the length of that vector. We want the distance that 4 plus 3i is from 0. Clearly, it's not going to be a distance of 4 plus 3i. What does that even mean? It's neither is it a distance of 4, it's more than 4. It's not 3, it's certainly more than 3. What in the world is it? And you might say to yourself, I hope you would say to yourself, hey, can't we just use the Pythagorean theorem? Who was that? That was not the imaginary student. It was one of you, yes, yelling at me through the internet. Yes, we can use the Pythagorean theorem. We have here a right triangle. Look at that. Do we know the length of this side? Well, sure. If we went 4 to the right and 3 up, then this must be a length of 4. If we went 4 to the right and 3 up, this must be a length of 3. Pythagorean theorem says that if you have a right triangle, then 3 squared plus 4 squared must equal c squared. So that's 9 plus 16 equals c squared. That's 25 equals c squared. Therefore, c must be the square root of 25. So c is 5. So that means, how far away is this point 4 plus 3i, how far away is it from 0? 5 units away. So the absolute value of 4 plus 3i is, surprise, surprise, it is 5. Let's do one in some other quadrant. I lean toward the first quadrant because everything's positive. But let's do one where we're in a different quadrant. Let's find the absolute value of, how about negative 3 plus 6i. No, I can't fit 6i in there. Negative 3 plus 2i. Negative 3 plus 2i. Where is negative 3 plus 2i? Negative 3 plus 2i. I'm now in the second quadrant. If you want to, make it into a vector. The question with absolute value is, how long is that vector? So again, we think of it as a right triangle. Yes, where this is clearly a right angle. And we know the length of this side. You say it's negative 3. Well, how long is that side really? Oh yeah, it's just 3. This side is 3. How long is this side? It's 2. Pythagorean theorem says 2 squared plus 3 squared equals my unknown length of the vector. I'll call it c squared. That's 4 plus 9 is c squared. That's 13 is c squared. Therefore, if 13 is c squared, what's c? Square root of 13. So what's the absolute value of the complex number negative 3 plus 2i? How far is negative 3 plus 2i from 0? It's square root of 13. So really, what are we doing? We're considering the 3 to be the length of one side of the triangle, the 2 to be the length of the other side of the triangle, and then we plug it into the Pythagorean theorem and we get the length of the vector. We get the absolute value of negative 3 plus 2i. We get the answer to how far away negative 3 plus 2i is away from 0. The meaning of absolute value, distance from 0, square root of 13. So do we have a formula for this? Well, of course we do. The formula for the absolute, well, here, next screen. The formula for absolute value of a plus bi. What do? We take this guy and square it. We take this guy and square it. But then that gives us c squared. We don't want c squared, we want c. Therefore, we take the square root of the whole thing, and there's your formula for absolute value of a complex number. Take your a value, square it. Take your b value, square it. Add the results, and take the square root of the answer, and you've got yourself the absolute value, the distance from 0 of a complex number. It comes straight from the Pythagorean theorem. If a squared plus b squared equals c squared, then c must be the square root of a squared plus b squared. Done. What's on my next screen? Okay, some practice. To find the absolute value of negative 5 plus 12i. And again, those who are not watching the videos might give me some wacky answer like, oh, it's going to be positive 5 plus 12i. What does that even mean? That's the distance from 0? We don't even know what an imaginary number means. Forget it. No, that's silly. You've got to pay attention here. Yes. To find the distance from 0 of this complex number in the coordinate plane, we take the negative 5 and square it. Negative 5 squared plus the coefficient, not the I, just the 12. 12 squared. And we take the square root of that, and that will be my absolute value, which gives me the square root of what? 25 plus 144. That's the square root of 169, and that happens to be exactly 13. Negative 5 plus 12i is 13 units away from the origin. The absolute value of negative 5 plus 12i is 13. Hey, it's quite possible if you know your geometry very well, you may recognize, hey, I know all about the 5, 12, 13 triangles. Yeah, if you've got legs of 5 and 12, that's one that back in geometry you were supposed to have memorized, that if you have legs of 5 and 12, you automatically know your hypotenuse will be 13. If you notice that, you're done. In fact, here, if your legs are 3 and 4, what do you know about the hypotenuse? It's going to be 5. But what if you don't see that trick right away? All right. Once again, we take the square root of a squared plus b squared, which is the square root of 25, which is 5. 4 minus 3i is 5 units away from the origin, away from 0. Absolute value of complex numbers. We use the Pythagorean theorem. Take the square root of a squared plus b squared. Nice. 3 points on the next test for everybody, right? Right. We're done. Your assignment, page 325, numbers 2 through 12 even. Real graph paper on those first 2 problems is required. For numbers 2 and 4, I want 2 separate coordinate planes and 3 points on each, just to clarify. I don't want to have one coordinate plane with 6 points all over there that I've got to sort out. No, I just want them on 2 separate coordinate planes, 3 points on each plane. Make my life easy, please. And I don't think there's anything on the next screen, which means we are done. A world record short section. And we'll see you next time. Goodbye.